everybody. This is uh, microcontroller class, and we are meeting amidst the coronavirus problem, and so we have digital classes for the rest of the syllabus until we start our regular classes. Now, as we have discussed a lot of things about programming in microcontroller ARM. And I remember these topics that we have discussed in the earlier classes, where we talked about writing and optimizing ARM assembly code. And optimization of given code is to make program to execute the instructions faster and by consuming less number of clock cycles and consuming less memory. And we have discussed a lot of things about what is exactly optimization is, and let me recall. There are three methods of there are three uh, uh, like three ways of optimizing the assembly code. One is through instruction scheduling and register allocation. And the third one is conditional execution. Now, instruction scheduling is rather, we should call it as instruction rescheduling, because once assembly code is given, if it is not optimal code, we have to reschedule the code so that the program becomes optimized, which consumes less number of clock cycles and consumes less memory. And register allocation is where we can rename the registers with the RN assembler directory. We'll see in the future classes, and we can use the available 15 or rather 12 programmable registers, that is R0 to R12, multiple times, so that we don't go shortage of these registers for programming. And there are conditional executions. We have discussed these things in the first module, where we have seen what is conditional execution, which are mnemonics which are suffixed after the instruction, which lets the instruction to execute only if this condition is true. And we'll discuss this in optimization too. And let me go to those topics that we have supposed to start, and these are the programs methods we have discussed, and this program also we discussed in the earlier classes. And let me go to the first technique of optimization of code. And here profiling is a tool which is to measure the proportion of time or processing cycles spent in each code. So here in the program that we write, if if you can measure the number of processing cycles that program has taken, that method is called as profiling. And we'll see this in future coming classes. But there's something called a cycle counter, which measures the number of clock cycles taken by a specific routine. Okay, and we'll discuss this in future. Let me go to optimization here, where the first technique is instruction scheduling. And this instruction scheduling is rescheduling rather, but let us discuss according to the syllabus. Now, before we understand what exactly instruction scheduling is, let us understand what is instruction pipeline timing. And you know what is the pipeline? The pipeline is a method of making two or more instructions execute parallelly, provided that we have that hardware that can support the different stages or operations that each instruction actually possesses to complete the instruction. And we have seen there are the three-stage pipeline of ARM7, which are fetch, decode, and execute. And we should know instruction pipeline timing and number of clock cycles needed to execute each instruction in advance before you go for rescheduling of instruction in programming. And we should also know conditional instructions, what we have discussed earlier. But conditional instructions take one clock cycle, and this is the point that we have to make here clear very, because conditional instructions take one clock cycle to execute if the condition is not met. In the sense, if the condition is not met, the conditional execution instruction take only one clock cycle. If condition is met, it has to go to that condition and go to that label and perform the instruction. So this will be discussed later. And if the instruction is not met, then the following rule will apply. So if the condition is not met, then there are some specific rules to calculate the number of clock cycles each instruction takes based on the categories of instructions. So let us see what are those categories of instructions for conditional execution. Not condition is not if condition is not met. So I believe this is quite readable here. Let us take a clear view of this. This table gives you a clear picture of different types of instructions, and number of clock cycles each type of instruction takes, and where some parameters or criteria to be met if why we take these extra instructions for execution. Let us take first category. Here we have ALU operations like addition, subtraction, and logical operations. And all these instructions, if there is no PC involved, in the sense that if any of this ALU instruction doesn't take one of the operand as a PC, like which is to be PR15 in our register file, if that is not involved, then this ALU instruction will take one clock cycle. Okay, and exceptional case is that shift. If there is a shift involved here, I mean, even shift is a logical instruction. If shift is involved here by an immediate value, the barrel shifter, we talk about barrel shifter here. If the barrel shifter is involved with a shift which is given by the immediate value, in that case, number of clock cycle is 1, which is to be consumed by this ALU instruction. And if the shift is specified, number of bits you have to shift in barrel shifter is specified by a register, then it will take one extra. Plus indicates along with this one, it take one extra clock cycle. And if there is no PC involved, in the sense that if the PC is involved here, like one of the operand is PC, then obviously there will be 2 additional clock cycles along with this one. So it will take 1 plus 2, 3 clock cycles if PC is involved in the instruction. If PC is not involved, is as one of the operand of this ALU instruction, then it would take 1 plus 1, that is totally 2 clock cycles if PC is not involved in ALU instructions. Now let us go to load and store load instructions, where we have LDM with single value. Here single value means load with single value. It's not load multiple. We'll see load multiple later. Now LDM with the single value, if PC is not involved, because if R15 or PC is not part of this instruction, then it would take 2 clock cycles. And there is one exception here. Assuming that assumption is that zero weight state memory for an uncased system, in the sense that if the system involved with it's not involved in cache operations, in the sense that if this instruction is not loaded from the cache, in that case or assuming no wait state for uncased system, in the sense if the instruction fetched from the not fetched from the cache, so there is no wait, assuming that there is no wait state of memory, means memory doesn't wait for the instruction to be loaded here or data to be loaded, if or a cache hit or for a cached system. So zero wait is assumed if cache is not involved, and if cache is involved, there will be hit. In the sense that cache hit is, I mean, you would have studied what is cache hit and miss in OS, but let me just briefly explain this here. Cache hit means if you're accessing data from a cache and actually you're accessing data from cache. If hit is successful, if the access is successful, then it's called cache hit, and for a cached system.